Good evening, students. So I am Mohana and I'll be discussing chemical bonding with you. So I have written down a lot of questions from JEE, NEET and from NCRT, and I have only written down those questions which come multiple times. It has come in various previous years. So I'll be discussing those questions with everybody. Okay, so while I discuss those questions, I'll be explaining the concept behind everything. So you don't need to worry. I'll be explaining each and everything behind the question, each and every concept behind the question. Okay, so let's get started. Okay, so the first question, as you can see over here, is which of the following Lewis representation of the molecules NF3O3 and HNO3 is correct? So you have been already given the Lewis representations, and we have to determine which one is correct. So there are four options. So the main thing about in here is the Lewis dot structure. So let us start with the Lewis dot structure. So what is the Lewis dot structure? So Lewis dot structure was created by a scientist called Lewis. So why he did that? He actually wanted to help others to visualize a covalent bond. He also helped himself. He created a model in how to visualize a covalent bond. So what did he do? He first postulated the octet rule. So what is the octet rule? So Lewis postulated that atoms achieve the stable octet when they are linked by a chemical bond. So that is the octet rule. Okay, chemical bond. So I guess I hope you can understand the writing. So the main thing over here is we have to understand the octet rule, that each and every atom in any structure, in any Lewis dot structure, has to attain its octet. So that is the main point. That is the first point of Lewis dot structure. And the second point is only the valence electrons take part in covalent bonding. So what is covalent bond? A covalent bond is a bond where two atoms, they share a pair of electrons. Okay, so let us see how can we draw a Lewis dot structure. Let us start with a simple example of carbon dioxide, CO2. So how can we do that? Carbon has an electronic configuration of 1s2, 2s2, 2p2, right? We know that from the chapter called atomic structure. And hydrogen has not hydrogen, in this case it is oxygen. So oxygen has an electronic configuration, it has an atomic number of 8. So it has an electronic configuration of 1s2, 2s2, 2p, 2p4, right? Yeah. So now the valence electrons over here, it is very important to note down the valence electrons. The valence electrons in carbon is 4. Why? Because it is this 2s and 2p. So 2 electrons from 2s and 2 electrons from 2p. And the valence electrons in oxygen is also from the 2s and 2p orbitals. So it has 2 electrons from 2s and 4 electrons from 2p. So now how do we draw the Lewis dot structure? The carbon is a central atom. As you can automatically understand, there is only one carbon and 2 oxygen atoms. So the carbon has to be the central atom because it is lesser in number. So let us draw the 4. Carbon has 4 valence electrons and oxygen over here has 4 plus 2, 6 valence electrons. So let us draw the valence electrons in the form of dots, and that is why it is known as Lewis dot structure. It is a dot structure. So how do we draw that? There are 2 electrons on this side of carbon and there are 2 electrons in the right hand side of carbon. Now let us draw the oxygen atoms. The oxygen atoms are on either side of carbon. So now oxygen has a valence electron of 6. So let us draw the valence electrons of oxygen. 1, 2, 3, 4, 5 and 6. And over here also we draw 1, 2, 3, 4, 5 and 6. So now the main thing about drawing a Lewis dot structure is that the atoms have to achieve the stable octet. This is the main thing which I just mentioned a few minutes before. So you see the oxygen only has 6 electrons in its valence shell. It has to reach 8 electrons to reach stability, to reach octet. So what it does, it covalently bonds with the neighboring carbon atom. So, and once it carries out the covalent bonding with the neighboring carbon atom, you can automatically see that it is also sharing its own pair of electrons, and in turn also taking carbon's electrons along with it. Okay, so the same thing happens to the right hand side as well. So the carbon and oxygen double bond is formed over here as well, because you see why double bond, because oxygen requires 2 electrons to fill its octet, because 6 plus 2 is 8. So these 2 electrons are coming from carbon, and similarly the oxygen on the right hand side also requires 2 electrons to fill its octet. So 6 plus 2 is 8, so it takes the other 2 electrons from the carbon, and the carbon gives 2 pair of electrons to the left hand side oxygen and 2 electrons to the right hand side oxygen. So the oxygens are now having a stable octet. We can clearly see that they are having a stable octet. But what about carbon? Is carbon having a stable octet? Let us count. So carbon has 2 electrons over here and it has 2 electrons over here. Okay, then that is 4. 2 plus 2, 4. Then it is also sharing 2 electrons with the left hand side oxygen. So that is 6, and here also it is sharing the right hand side oxygen's electrons as well. So another 2 electrons, so 2 plus 2 plus 2 plus 2, which is 8. So we can safely say that even carbon over here has reached its stable octet. So this is how you draw the Lewis dot structure. So let us see what was our question. The question was, we have to explain which of the following Lewis representations of the molecules NF3O3 and HNO3 is correct. Okay, so let us have a look. Let us start from the third structure. From the third structure, what is it? It is HNO3. This is a structure of HNO3. So nitrogen, let us write out the electronic configuration of nitrogen, and that is 1s2, 2s2, what is and this is 2p3, because nitrogen has an atomic number of 7. Okay, so now, and the oxygens we have just seen, oxygen has 1s2, 2s2, 2p4. So it has 6 valence electrons, and nitrogen has 5 valence electrons. And hydrogen, you know very well that hydrogen is only 1s1, so it has only 1 valence electron. So now let us draw this structure. How can we form this? Okay, so nitrogen is in the middle, we can see over here, and oxygen is in one side, in the left hand side, and the other oxygen is in the right hand side. Let us forget the bottom oxygen for the time being. Let us just try to complete nitrogen's octet first. So nitrogen has 5 valence electrons. So how many electrons does it require to complete its octet? 8 minus 5, 8 minus 5 is 3. So nitrogen requires 3 electrons to complete its octet. So let us see, nitrogen has 1, 2, 3, 4 and 5. So, and the oxygens over here, they are again what? They require 2 valence electrons, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 3, 4, 5, 6. Okay, now let us draw the bonds. I find this part very interesting. So you see, this oxygen wants its octet to be filled, and nitrogen also wants 3 electrons to complete its octet. So nitrogen shares 2 electrons with this oxygen. So after sharing 2 electrons with this oxygen's octet is filled. So it is stable. This octet is filled. Nitrogen's octet is still not filled. So what it does, it again forms a single bond with the right hand side oxygen. Okay, so now we can clearly see that nitrogen's octet is now filled, the octet filled. But what about the oxygen over here? The oxygen over here is not stable. It is not satiated. So what it does, it needs 1 more electron to complete its octet. So it has a hydrogen over here. It has a hydrogen over here, and the hydrogen also needs only 1 electron to complete its octet. So now, now everything is fine. The hydrogen had it was required by the hydrogen to complete to require one electron. So hydrogen now has one electron, oxygen also has one electron, then this oxygen is also stable because it has reached its octet. Sorry, just a minute. Yeah, octet. And this hydrogen has also reached its duplet. Hydrogen doesn't reach octet. Hydrogen is the only atom apart from helium that reaches duplet to attain stability. So this is a fact that hydrogen only has electrons in its 1s orbital, so it will only try to fill up its 1s. It will not expand beyond that. So hydrogen fills its duplet. But we can clearly see there is another oxygen over here. So this oxygen, there is no requirement for nitrogen to have this oxygen because nitrogen is already stable. But since it is this oxygen is present and this oxygen is not satiated, this oxygen still requires 2 electrons to complete its octet. So what nitrogen, you know what nitrogen exactly does? Nitrogen is very philanthropic. Nitrogen loves to donate to people. So what nitrogen does, it takes pity on the oxygen because the oxygen has less number of electrons, it is poor. So the nitrogen molecule donates to it. So this is what we know as the coordinate covalent bond or the coordinate bond. We also call it the dative bond. Okay, so this is the dative bond, and as a result of that, as a result of dative bonding, nitrogen attains a positive charge. So nitrogen over here has attained a positive charge, and since the oxygen has received 2 electrons from nitrogen, you see there is sharing of electrons is not occurring over here. Nitrogen is donating it but not fully. Nitrogen is donating to this oxygen as long as oxygen is bonded with it. Okay, so nitrogen is donating partially to oxygen. It is also retaining the electrons within itself, but since it is donating, that's why nitrogen is achieving a positive charge and the oxygen over here is attaining a negative charge because it is becoming partially ionic. The bond is becoming partially ionic. So as a result, what happens over here? This dative bond, in this dative bond, nitrogen this has a positive charge and the oxygen acquires a negative charge. So you can see over here, they have not put a negative charge over here. So this is incorrect. This structure is incorrect. So we can cross it over. Now what about the structure 2? Let us see the bonding in ozone. The structure 2. Okay. So this is ozone. You can clearly see this is an O3 molecule. So this is ozone. So the oxygen O3. Let us draw the oxygen. There are 3 oxygens over here. Now we know that oxygen has 6 electron valence electrons. It requires 2 electrons to complete its octet. So what happens? These two oxygens are very happy because they have found each other and now they can complete their octet. But what about this oxygen? This oxygen, these 2 oxygens are very satiated between themselves. They don't really require this oxygen. But again, like I said, some molecules, they have a lot of pity, so they love to donate. So this oxygen saw that this lone oxygen is not having any partner, so it took pity and it starts to donate. So as a result, what happens? This is also a dative bond, and since due to the dative bond, since this oxygen is donating, this oxygen is acquiring a positive charge and this is acquiring a negative charge. So this is the complete Lewis dot structure. Okay. But do we have the charges over here? No, we don't have the charges. So this representation is also incorrect. Now let us look at the first representation. I am drawing over here. So first representation is NF3. It was NF3. So let us see how the NF3 molecule looks like. So now we have already discussed that. We have already discussed that nitrogen has 5 valence electrons and it requires only 3 valence electrons to complete its octet. So what it does, and fluorine, let us look at the electronic configuration of fluorine. It is 1s2, 2s2 and 2p5. So it requires how many electrons? The valence electrons over here, 5 plus 2, 7. So it requires 8 minus 7 is equal to 1. It requires only 1 electron to complete its octet. So what it does? Nitrogen requires 3. So let me draw the lone pairs of nitrogen, 1, 2, 3, 4, 5. So they are a very complete pair, complete match. And over here the fluorine has 1, 2, 3, 4, 5, 6, 7. So let us do the bond, let us write the bond. And you can see similarly for this fluorine, I'm not drawing the electrons for every one, you can understand. So you can clearly see that there is no charge buildup, and even if it was there, it would have been written, but whatever. This is a complete structure. Is this structure matching with the structure given in the question? Yes, it is, because you see all the fluorines are having their octet complete, nitrogen is also having its octet complete, so it is a correct structure. Okay, so this first structure is the correct structure, so which is the correct option? Only one. So this A option is the correct option. Okay, so I hope you have understood. I am moving on to the next question. Which of the following pair of molecules contain odd electron molecule and an expanded octet molecule? So this is very interesting. Again, you need to know. You need to find out odd electron molecule. You need to know how to write down the Lewis dot structure of any atom, of any molecule. Okay, so let's get started again. What are the options which we have? We have BCl3 and SF6. Let us see. BCl3. BCl3. So what is the structure of BCl3? Boron. Boron. What is the electronic configuration of boron? 1s2. Hydrogen, helium, lithium, beryllium, boron. So it is 1s2, 2s2, 2p1. And chlorine is in the fluorine group. So if fluorine had, what to say? Fluorine had what? 1s2, 2s2, 2p5, right? So chlorine will also have something like, I am not writing the other electrons, I am just writing the last pair. It is 3s2, 3p5. I am not writing the other electrons. Okay. So fluorine is having something over here, but we are not involving these electrons. We are not involving all these electrons because they are the inner electrons. So they do not participate in bonding. So only 3s2, 3p5. So these valence electrons, they participate in bonding. So 5 plus 2, 7. So 7 valence electrons. So we have 8 minus 7, which is equal to 1. So chlorine only requires, just like fluorine, fluorine requires 1 electron to complete its octet. So let us see how the bonding here occurs. So boron has, like I said, it has, see over here clearly 2 plus 1. 2 plus 1 is 3 valence electrons. So boron has 3 valence electrons. It requires a lot of electrons to complete its octet. Boron is really electron deficient. It requires about 5 electrons to complete its octet. But let's see how the bonding is taking place. So there is chlorine over here, and chlorine over here. So chlorine only requires 1 electron. So let us draw the electrons of chlorine. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. And boron also has 3 electrons, 1, 2 and 3. Just a minute. Yeah. So we can carefully create the bond over here. The single bond over here. This is BCl3. Okay, so we can clearly see, yeah, you can say that boron is not reaching its octet because 1, 2, 3, 4, 5, 6. So boron is not reaching its octet. Boron only has 6 electrons in its valence orbital. It is not reaching 8. So we cannot say that it is a case of expanded octet because it is not completing its octet at all. So how can it be expanded? Okay, so and neither it is an odd electron molecule. They are all satiated. Nobody is odd over here. They are all in pairs. Okay, so now SF6, let us quickly see the molecule of SF6. SF6, how do we draw that? Sulfur is in the oxygen group. If sulfur is in the oxygen group, if oxygen has 2 valence electrons, the properties of group is such that if oxygen has 2 valence electrons, then sulfur will also have 2 valence electrons. Because they will require 2 valence electrons to complete their octet. Oxygen has 6 valence electrons. Over here sulfur also has 6 valence electrons. So oxygen or sulfur will require 2 valence electrons to complete their octet. So since sulfur is given over here, let us draw it. Sulfur, so, and the fluorine. I am drawing all the fluorine. We have just discussed about fluorine. Fluorine only requires 1 electron to complete its octet and sulfur requires 2 electrons. So 1, 2, 3, 4, 5 and 6. Okay. So just a minute, I have drawn it in a very expanded way. 4, 5 and 6, yeah. And the fluorine also requires 1 electron. So all the other electrons over here, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Let's draw it. 1, 2, 3, 4, 5, 6. So we can clearly see that all the fluorines are very stable because they have obtained their octet over here. But what about sulfur? I just mentioned that sulfur has 6 valence electrons. It requires only 2 electrons to complete its octet. But what is happening over here? Sulfur is not just bonding with 2 more electrons. It is acquiring many more than 2. It is acquiring, I am counting, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So through covalent bonding, sulfur has a total of 12 valence electrons now. It initially had 6, but it is taking 6 more through covalent bonding. So what do we call this case? This is a case of expanded octet. Why? Because sulfur is expanding its octet. So sulfur is expanding its octet. So this is a clear case of expanded octet. So we have found out one criteria, expanded octet. So now we have to find out the odd electron molecules. So SF6, wherever we see SF6, that will be the case of expanded octet. So as this, here we have an SF6 and here also we have an SF6. Okay, so we got that. Now, but since BCl3 is not an odd electron molecule case, so we are cancelling out this option. Okay, so it can be, and see here also BCl3 is not a case of odd electron molecule, so we are cancelling out the D option as well. So we have to, in order to complete any question quickly, we have to eliminate. We have to proceed by the method of elimination because the time is very less in exams, during the exams. Okay, so now let us see options B and C. So let's start with B. Just a minute, let me add a page. Okay. This, what did we have? We had NO. Okay. So the B had NO and H2SO4. Let us see how does NO bond. So it is very important to know the Lewis dot structure because questions based on Lewis dot structure come a lot in JEE. Okay, so it is very important. So NO. So how does NO look like? Nitrogen, I have mentioned a lot of times, nitrogen has 5 valence electrons. So 1, 2, 3, 4, 5. So nitrogen has 5 valence electrons. Very clearly you can see over here. And oxygen has 6 valence electrons. Oxygen requires 2 valence electrons to complete its octet and nitrogen requires 3 valence electrons to complete its octet. Okay. So let us complete the bonding over here. 1, 2, 3, 4, 5, 6. Okay. So what happens over here is there is a double bond between nitrogen and oxygen is fully satiated but nitrogen is not. Okay, so nitrogen is not, so it becomes an odd electron molecule. What happens over there? A triple bond also starts to form between the nitrogen and the oxygen moiety. But this odd electron, you see this electron is not paired. This electron becomes unpaired and this triple bond begins to form. Why? Because since this nitrogen is not satiated, its octet is not fully filled, so this oxygen again takes a pity on this nitrogen and it starts to form the triple bond. But the main important thing over here is this electron remains unpaired no matter what. So what happens over here is unpaired electron. So this is a very classic case of odd electron molecule. Okay, and now let us see the case of, so we have found the odd electron molecule. So wherever we see NO, just a minute, yeah, wherever we see NO, over here we have NO over here, only in the B option and in the D option. D option we had already cancelled out because BCl3 was not the answer. It did not have an expanded octet. So NO, I think B will be the answer. So let us see if H2SO4 has an expanded octet or not. Then only we will be able to Verify your answer. So H2SO4, S double bond O, double bond O. There are 4 oxygen. S double bond O, double bond O, OH and OH. It looks like this. Again, I have just directly written out the bonds. Let us see how the octet is occurring. So oxygen, as I said, it requires 2 electrons to complete its octet. So here 1 electron it is using with hydrogen, and here 1 electron it is sharing with sulfur. Okay, so we can clearly see I am not drawing the other bonds of oxygen. I think it is self-explanatory because I have discussed a lot of questions. Okay, so here oxygen over here. Let us see the right hand side oxygen. Here also the oxygen is sharing 1 electron with sulfur and 1 electron with hydrogen, and so this oxygen also reaches its octet, and this hydrogen also reaches its octet. So it is fully satiated. So what about the sulfur now? The main thing comes over here. That sulfur requires only 2 electrons. It is in the oxygen group. So it requires only 2 electrons to complete its octet. So sulfur has 6 valence electrons just like oxygen. So what the sulfur does, it bonds with 2 more oxygens. And these 2 oxygens are also sharing 2 electrons with sulfur. So they are also satiated. They are also stable. But sulfur, you can see clearly, it is sharing a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 valence electrons. So again we can safely say that this sulfur here over here is a classic case of expanded octet. So we can safely say that this option B is the correct answer. We had an unpaired electron, so that is NO is an odd electron molecule, and H2SO4 is a case of expanded octet. Okay. Okay, so let's move on to the next question. Which of the following is an electron deficient molecule? We have C2H6, B2H6, SiH4 and PH3. Again, we need to know how the molecules look like. C2H6, C2, which means there are 2 carbon atoms. Now carbon has a valency of 4. It has, the number of valence electrons in carbon is 4. So it requires 4 more electrons. It requires to bond with 4 more electrons. So carbon has a valency of 1s2, 2s2, 2p2. Okay, so there are 4 electrons over here. You can clearly see. So it requires 4 more electrons to reach its octet. So it will, each carbon will then what? They will bond with 3 more hydrogens, because I have already shown the carbon-carbon bond. The carbon-carbon bond has to happen because there are 2 carbons. So 1 electron, this carbon is sharing 1 electron with this carbon. There are 4 more electrons, 1, 2, 3. 1, 2, 3. So let's draw the hydrogens, this hydrogen, and this hydrogen over here, and similarly on the other side. So these hydrogen also have 1 electron each. So all the time you don't have to draw the Lewis dot structure. You need to, it is very important in JEE that you know the structure beforehand, because it is very time taking. I am just drawing the Lewis dot structure in order to clear your concept of chemical bonding, how the structures actually are formed. But you will not have so much of time to figure out the electrons and how the electrons are bonding. So this is just a concept building session. Okay, so this C2H6 looks like this. Okay, so we can clearly see that this is not an electron deficient molecule. What is an electron deficient molecule? It is a molecule which has less number of electrons. Deficient means less. So carbon is fully satiated, and hydrogen is also fully satiated because everybody has its octet. So let us move on to the next option, which is B2H6. Okay, before moving on to B2H6, let me do the other structures as well quickly. Structure C, SiH4. So silicon is in carbon group. So just like carbon, silicon also has a number of valence electrons of silicon is 4. So it will require 4 more electrons, 4 valence electrons. So it will require 4 more electrons to reach its octet. So let us see how does silicon look like. I am not concentrating on the geometry because geometry will be doing shortly bit after. Okay, so the hydrogens are over here. I am not explaining geometry right now. I will be explaining after some time. Okay, so silicon has to bond with 4 more hydrogen atoms to obtain an octet, to reach an octet. So we can see clearly that silicon is reaching an octet. So it is not electron deficient. And about the option D, we have PH3. Phosphorus is in which group? Phosphorus is in the nitrogen group, nitrogen phosphorus. So it is below nitrogen. So the groups have similar number of valence electrons. They have identical number of valence electrons. So if nitrogen has 5 valence electrons, phosphorus also has 5 valence electrons, and if phosphorus has 5 valence electrons, it requires to bond with 3 more atoms or carry out 3 bonds to reach its octet. Okay, so phosphorus is over here, and phosphorus has 1, 2, 3, 4, 5. We have 3 hydrogen atoms. Very conveniently, phosphorus bonds with them. So what happens? We have 3 bonds. So phosphorus is stable. It has reached its octet, and hydrogens also have its duplet. Now what is left? B2H6. Let me show. That is because B2H6 is the answer. That's why I showed you at last. B2H6. How does B2H6 look like? There are 2 boron atoms. So we will draw 2 borons like this. And there are 6 hydrogen atoms. So if we divide the hydrogen by 2 between the 2 boron atoms, each boron atom will have to get 3 hydrogen atoms, right? So over here there are 2 hydrogen atoms bonding. Okay, just a minute. I just mentioned before that boron has a electronic configuration of 1s2, 2s2 and 2p1. So it has a number of valence electrons is 3. So it requires 8 minus 3, which is 5 valence electrons to complete its octet. But will it be able to reach it? Let us see. Okay. So boron has 1 valence electron over here, 1 valence electron over here, and it is bonding with the hydrogen, neighboring hydrogen atom, and it is trying to get satiated. Now boron only has another hydrogen, another valence electron. So what it does with that? Let us see. Okay, over here also let us draw the other 2 hydrogen atoms of boron. Okay, so now we have already drawn 4 hydrogen atoms of B2H6. So now we only have 2 hydrogens left. What to do with those 2 hydrogens? We put it in the middle. So what these 2 hydrogen atoms do, they are actually very confused. They don't know which boron atom to approach. So they decide that okay, we will bond with both the boron atoms. So what they do, but hydrogen only has 1 electron. So how can that happen? Boron also has 1 electron, hydrogen also has 1 electron. So what happens over here? A bonding occurs definitely. A bonding over here occurs, or maybe I'll draw it with the black pen. That is a normal bond, but this hydrogen over here, it also wants to bond with a neighboring boron, but it does not have any electrons. So what happens over here? It tries to carry out a 3-center 2-electron bond. It is a 3-center 2-electron bond. It doesn't really have any electrons, but they are together in a very harmonic way. This hydrogen atoms is bonded with both the boron atoms. So this is not a partial bond. I will thicken the bond because this is a complete bond. This is not very strong because it is not held together by electrons, but it is known as a 3-centered 2-electron bond because there are 3 centers, boron, hydrogen and boron, but there are only 2 electrons which is shared between these 3 centers. I hope you understood this. So now you can see the number of atoms in boron is octet complete. Let us see that. So the number of atoms which are present around boron is 1, 2, 3, 4, 5, 6, and here there are no electrons. We can see there are no electrons over here. Since there are no electrons, there are only 6 electrons in the outermost valence shell of boron. So what can we say? That boron has not completed its octet. No octet. That means what was the question? So this B2H6 molecule is electron deficient. So the answer is B over here. B2H6 is electron deficient. I hope you are getting it. Okay, so now let us go to this. In PO4 3 minus ion, the formal charge on the oxygen atom of PO4 PO bond is what? So in order to find out the formal charge, what you first require is to know the formula of a formal charge. The formal charge, let me write it down. Formal charge on an atom in a Lewis structure is equal to total number of valence electrons in the free atom minus total number of non-bonding or lone pairs of electrons minus half the number of total number of, just a minute, bonding electrons or shared pair of electrons. Okay, so what is the meaning of that? Let me explain with this example only. Let me do the phosphate one, then only you will understand. We will get the answer also. Okay, so phosphate, how does phosphate look like exactly? P, there are 4 oxygen atoms, 1, 2, 3, 4. Now we know that the phosphate, phosphorus has 5 valence electrons and phosphorus requires 3 to complete its octet, right? Because it is in the nitrogen group. So how does phosphate exactly look like? PO, P double bond O, 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 O. Now you will ask why phosphate is looking like this. Phosphate only requires 3 bonds to complete its octet. We are having 1, 2, 3, 4, 5. 5 bonds are there. So what is this case? This is a classic case of expanded octet, right? We just discussed it with SF6 and H2SO4 a few minutes earlier. So this is a classic case of expanded octet. So phosphorus has bonded with more atoms than it really requires. Why? Because it has lots of oxygen atoms around it, so it likes to mingle with lots of people. That is the only reason. Okay, so the chemical reason behind it is phosphorus has vacant p orbitals for bonding. Okay, so that is also a reason. So now what happens over here? Let me erase this because the answer will require space. Okay, so what happens? The phosphorus over here, the phosphate group looks like this. So the ion is 1, 2, 3, 3 minus, phosphate 3 minus. Okay, so we know there is a phenomenon called resonance. We have already encountered it. So oxygen goes over here and it comes over here. So what happens? P, O minus, double bond O, O minus, O minus, and then this oxygen comes over here and this opens up, and this goes on and on. This oxygen then comes over here, this opens up, and we get 4 resonance structures. Okay, so but what we require over here is the formal charge. The formal charge on an atom in a Lewis structure. So how to obtain that? So how will we obtain the formal charge of an atom in a Lewis structure? Okay, so formal charge is asked of only the oxygen atom of a PO bond, not phosphorus. They are asked of the oxygen atom. So let us see all the resonance structures first. P double O minus, double bond O, O minus, and again if this becomes a double bond, then we have P O minus, O minus, O minus, double bond O. So now what do we get? We get 4 resonance structures. So what is the resonance hybrid over here? P double bond, P single bond O, and each PO bond has a double bond character. We can clearly see over here that each PO bond has a double bond character. So what will be the formal charge of oxygen? Technically what will it be? How will we calculate? Because you can clearly see that in the first structure oxygen has a negative -1. In the second structure oxygen has this particular oxygen is 0 in the first structure. Now in the second structure this particular oxygen has a -1 charge. In this third structure also this particular oxygen has a negative charge, and in this fourth structure also this particular oxygen has a -1 charge. So how to find out the formal charge? So what over here what we will do exactly? We will try to find out the average formal charge. What is the average formal charge? So there are 4 resonance structure. Number of resonance structure is 4. We are having 4 resonance structures. But what is the total charge? What is the total charge? Here it was 0. So let us calculate total charge on O is equal to, here it was, here in the first structure it was 0. So let us add all the structures, all the charges of all the atoms in the all the oxygen, all the structures, oxygen atoms, whatever we have, this particular, just get hold of only one particular oxygen atom. Get hold of only one particular oxygen atom. Like in the first structure, we have gotten hold of only this first oxygen atom. So now, so we will in the progressing in the second structure also we will look at only this oxygen atom. In the third structure also we will look at only this oxygen atom. In the fourth structure also we will only look at this oxygen atom. Okay, so in the all the four structures we will look at the same oxygen atom and try to add up its the respective charge. So in the first structure this oxygen atom had 0 charge. In the second structure this oxygen atom has negative -1 charge. Third structure it has -1. Fourth structure also it has -1. So the total charge over here is -3. So now how do we find out the, let me come to a new page. So what is the total charge? So total formal charge. Total formal charge on oxygen is what? It is the total charge on oxygen by the number of resonating structures. So we had found out the total charge on oxygen, just a few minutes back we found out the total charge on oxygen is -3 and the -3 over here, and the number of resonance structures was 4. So let us write that down. So -3, number of resonating structure was 4. So what is -3 by 4? It is -0.75. If you calculate this, this is -0.75. Do we have such an answer? Let us see. Yes, we have such an answer. This option C. This option C is the correct answer. So you can see that this formula was not required because in here we have multiple resonance structures. So they have asked us to find out the oxygen atom of the PO bond. Since there are multiple resonance structures, we need to actually find out the average. We need to find out the average formal charge. Why? Because the actual structure of phosphate is this resonance hybrid. The resonance hybrid is always the actual structure of any molecule. Resonance hybrid is the actual structure. So in the resonance hybrid, how do we find out the charge? By this formula, which I wrote down right now. This is the actual formula. Okay, I guess it is understood, and I'm moving on to the next question. Okay, yes. So this is a question, this is a very important question from NEET 2022. Amongst the following, which one will have maximum lone pair electron repulsion? So even if it is from NEET, it is a very important question for JEE as well. So let's see. Okay, so among the following, which one has the maximum lone pair electron repulsion? So where do we encounter this word? This word comes from a very famous theory known as, let me write it down over here. Yeah, it is VSEPR theory. So what is the full form of this theory? Valence shell electron pair repulsion theory. Okay, so what does this theory say? This theory usually helps us to find out the geometry and the shape of molecules, of simple molecules, but it does not provide us with any experimental evidence or theoretical evidence. It just shows us that it happens. This is IF5 looks like this, SF4 looks like this. It just tells us, but it does not tell us how it is happening. So this is a very useful tool because it is very difficult otherwise to predict molecules. So this helps us predict the geometry and shape of the molecules. Okay, so there is another thing which VSEPR theory tells us, that is it tries to explain the formation of this different compounds, the geometry and shape of the different compounds through a main point, which is that lone pair repulsion, lone pair repulsions are greater then lone pair bond pair repulsions, which is again greater than bond pair repulsions. Okay, so this is the main thing. So the VSEPR theory uses this postulate. This is a postulate. So this postulate to determine, to predict the structures of different molecules, you can say. Okay. So let us see how do we do that. I have a very short trick on how to find that out. So first, hybridization, finding out hybridization of the molecule is also very important, and through the hybridization of the molecule you will be able to find out the geometry and shape of the structures. So hybridization is a concept. Let me recap that hybridization is a concept which we had obtained, which we have learned through VBT, valence bond theory. Yeah, we had obtained this concept through valence bond theory. Okay, so this concept was obtained through valence bond theory. So valence bond theory had introduced to us the concept of atomic orbitals. So valence bond theory had told us that when two atoms are coming together, like A and B, let us assume A and B are two atoms, they are coming together to form a bond which is AB, then what happens? The atomic orbitals of A and the atomic orbitals of B, they bond, they come overlap, they come together and they overlap. And this overlap can happen in two ways. This overlap can happen in either head on head, yeah, head on head overlap, or parallel overlap, or it can be also known as side by side overlap. So there are two ways where this how this overlap can occur, and if the overlap is head on head, we get a sigma bond, and if the overlap is parallel, we get a pi bond. Okay. Okay, so this is the main thing which you needed to understand about VBT, and I'll be talking about hybridization as well as VSEPR theory. So I will be telling you a short trick. So let us write down serial number. So many a times it is very difficult to find out number of lone pairs or bond pairs in a molecule. So I'll be showing you a short trick, and then only you will be able to predict the molecules, the structures and geometry very easily. So serial number, number of valence electrons of central atom. Okay. Number of monovalent atoms. Number of monovalent atoms around central atom. Around central atom. And okay, so if they are monovalent atoms, their contribution is 1 for monovalent atoms. Let me write that down, for monovalent, or maybe I should write it in the previous page. So there is some space left over here. I should write it over here. Yeah. So for monovalent atoms, if X is monovalent, then the contribution is 1. But if X is divalent, what are divalent atoms? Like O2 minus, S2 minus. So the contribution is 0. What is this contribution? I'll be talking about it right now. Okay. So number of monovalent atoms around central atom. Okay. Now number of valence electrons of central atom, number of monovalent atoms around the central atom, and then we have the hybridization, or the total number. By 2. Okay, yeah. Now we then have the hybridization, or hybridization, and then we have the geometry, and then we have the shape. and then we have the shape. Let me try to shorten this part down. Let me see if I can do this or not. Okay. Okay. So let us see how this happens. So for serial number 1, number of valence electrons of central atom. So if we are talking about hybridization, which is sp, and what are the examples of sp? Let us take the example of just a minute. Instead of serial number, I should write type of atom. Type of atom. I'm writing the examples over here only. Okay. So this is C2H2, which is alkyne. I guess it is very clumsy. I think I should do in a different way. I'm directly drawing it over here. It is very clumsy. Okay, so what happens over here? Just see. We have C2H2, right? We have C2H2. We know this is alkyne. So it looks somewhat over like this. It has a triple bond. Okay. So how to find out its hybridization? What is the central atom over here? Or any kind of sp. We also have BeF2 or BeH2. What is the central atom over here? BeH2. The central atom is beryllium, isn't it? Beryllium is what? The electronic configuration of beryllium is 1s2, 2s2. Okay. So the valence number of valence electron is 2. This is the valence electron. So what it does? It bonds with 2 more hydrogen atoms. So now what happens is that BeH2, how will it exactly look like? So the number of valence electrons of beryllium is 2. So it is bonding with 2 more monovalent atoms. This is hydrogen. You can see it is hydrogen over here. It is bonding with 2 more monovalent atoms. The 2 plus 2, it is 4. 4 is the total number. If we divide 4 by 2, it is 2. We are getting 2. So which hybridization? Which hybridization has 2 bonds? sp hybridization. So this is how you can predict. How sp? How can we come at sp? Because there is one s and one p. So there are 2 bonds. Okay, there is only one s and one p. It can't be less than that, right? This is the least hybridization which molecule can obtain. So there is one s and one p. So that is why it has 2 bonds. So we can totally understand that beryllium will be in the central atom, and hydrogen will be monovalent, and it will be straight around it. And beryllium does not have any lone pair. So since this is sp hybridized, and so this will be linear. You can clearly see that the molecule is linear. Okay. Now let us take the example of another molecule example, which is sp2, which is BF3. So I told you already this is sp2. How will you find out that this is sp2 or not? So boron has an electronic configuration of 1s2, 2s2, 2p1. So the valence electrons are 3. We know that. So how does so 3 valence electrons? So number of valence electrons is equal to 3 plus number of monovalent atoms. Here we have monovalent atoms, number is 3. So 3 plus 3 is 6. 6 by 2 is 3. So 3 is the number of bonds. Number of bonds formed by boron. There are 3 bonds formed by boron. So B forms 3 bonds with fluorine, and anything which forms 3 bonds, 3. What hybridization has 3 units in it? sp2, 1s and 2p. See, 1 plus 2. 1 plus 2 is 3. So by that way, you can see if this number, this is sometimes called the steric number. If the steric number is sp2, if the steric number is 3, then 3 means 1s and 2p. That means that it is 3. Okay, so after finding out the steric number, you will be able to determine what is the hybridization of the molecule given. And how will you determine the steric number? through then adding the number of valence electrons plus the number of monovalent atoms by 2. Okay. Now that the another example is example of an sp3 hybridized molecule, which is CH4. So how will we find out this is sp3 hybridized? The central atom over here. First we need to identify the central atom. Over here the central atom is what? It is carbon. So carbon is 1s2, 2s2, 2p, 2p2, right? So now what happens? There are 4 valence electrons in carbon. So number of valence electrons is 4 plus number of monovalent atoms over here is 4 is equal to 8. The total number by 2, which is 4. So 4 is the number of which hybridization? sp3. Why? Because it is formed from 1s and 3p orbitals. Not 3p orbital, it is 3p orbitals. Okay, I guess you understand. 1s and 3p orbitals, they combine to form sp3 hybridization. So I guess you understand that this sp3 hybridization will always have a steric number of 4. Okay, and that we will get through number of valence electrons of the central atom, which is carbon, and the number of monovalent atoms. In this case it is hydrogen atom. Now if we try to find out for another molecule like PCl5. What is PCl5? Let us find out how. Phosphorus over here is a central atom. You have to first identify the central atom. So now phosphorus has a electronic configuration similar to nitrogen, right? So phosphorus, I don't need to write down the electronic configuration of phosphorus because it is not required. You know that it is an electronic configuration similar to nitrogen. So number of valence electron of phosphorus is 5. So number of valence electrons 5 plus number of monovalent atom over here is 5, which is 5 plus 5 is 10. 10 by 2 is 5. So here 5 has what? 5 has sp3d hybridization, because p can only be a maximum of 3. We cannot expand p above 3. So the next orbital which comes after p is d. So we have sp3d hybridization. Okay. So this is what we have. And now because one s, 3p orbitals and 1d orbital. So these all these come together to form the number 5, and that is why whenever we get the steric number 5, we can automatically assume conclude that this particular orbital has an sp3, this particular molecule has an sp3d hybridization. I hope it is clear. And then we have after sp3d we have sf6. Okay, so sf6, what is the central atom over here? It is this sulfur. So sulfur has a similar electronic configuration to oxygen. So the number of valence electrons over here is 6. So let us again calculate the steric number. 6 plus 6 is equal to number of monovalent atoms over here is 6, is 12 by 2, which is 6. So 6 is the number of which hybridization? sp3d2. Okay, so sp3d2, this is the 6 is the number of this hybridization. So sp3d2, because 5 was for sp3d. So if we need to increase one number, so that will be d2. So there will be 2 d orbitals involved. Okay, so this is, I think it is very clear. Okay, and now we have what do we have after sp3d2? We have IF7. Okay, so I over here has number of it is the central atom, and it is the number of valence electrons over here is 7. So 7 plus the number of monovalent atoms is 7 is equal to 14. 14 by 2 is 7. So since the steric number is 7, we can just increase one more d electron because there are 5 d orbitals, so we can easily increase one more electron. So the hybridization of IF7 will be sp3d3, because 1s, 3p orbital and 3d orbitals, they form sp3d3. So the steric number 7 will show sp3d3 orbital hybridization. Sir, okay. So I just taught you how to find out the hybridization of each molecule very easily, just by finding out the number of valence electrons and adding it with the number of monovalent atoms and dividing it by 2. and whatever number you get, it is a static number, and with equivalent to that, you have to find out the hybridization. If it comes 6, then you have to see which hybridization will add up to the letters. The number of letters will add up to the number of 6. In case of 6, the number of letters which adds up to 6 is sp3d2. Okay. Now, I just told you about hybridization, but what about shape and geometry? So let us go back from the beginning. We were talking about BH2, right? So BH2, I told you it is linear. How it is? Is it linear? Because it is sp hybridized. Okay. I just explained it like that. But how? Does it have any other option other than being linear? No, it doesn't have. Because sp hybridization has a bond angle of 180 degrees. So these two hydrogen atoms have to be at 180 degrees to each other. It has no other option. Okay. So this sp, if something is sp hybridized, it has to be linear. There is no other option. It cannot be 90 degrees to each other. It cannot be that way, because the sp orbitals are 180 degrees away from each other. Okay. Now what about BF3? What is the shape? Here the geometry and shape both are linear. Let me write it down. The geometry and shape both are linear. There is no discrepancy over here. What about BF3? In BF3 we have sp2 hybridization, and sp2 hybridization over here, it is trigonal planar. It is trigonal planar. Okay, this is trigonal planar. I hope it is clear. Okay. So, and this is the geometry. This is both the geometry and shape. And for CH4, for sp3 hybridization, it is tetrahedral. For sp3d hybridization, it is trigonal bipyramidal. Trigonal bipyramidal. And for sp3d2, it is octahedral. And for IF7, it is pentagonal bipyramidal. I am talking about both the geometries and shapes, but there are some examples where the geometry and shape does not correspond with each other. Okay, so I will talk about that later. Let us solve this. We have already delayed this question a lot, so let us solve this question first. Okay. Okay, so let us see. We have IF5, SF4, XCF2 and CLF3, and we have to find out which one has the maximum lone pair repulsion. Let us draw out these these molecules first. Let me erase this entire thing. Okay. Let us start with option A, which is IF5. IF5. So how do we find out the hybridization first? We have to first draw the structure. In order to complete this question, how to approach this question? We have to find out the number of maximum lone pair repulsions. So in order to find out the number of maximum lone pair electronic repulsions, what do we have to do? We have to first draw the structure. We have to see how many number of lone pairs are there, and then only we will be able to do something. We will be able to find out the number of lone pairs, electronic repulsions taking place over here. Okay, so let's get started. What is the central atom over here? It is I. It is iodine. So the central atom iodine, what is the number of valence electrons over here? So if you clearly try to remember, it is the same group as fluorine, chlorine, bromine, iodine. So if fluorine has a number of valence electrons of 7, iodine has a number of valence electrons is 7. Okay, so 7 plus what is the number of ligands of monovalent atoms? It is 5. So 7 plus 5 is what? 7, 8, 9, 10, 11, 12. So it is 12. 12 by 2, which is 6. So the steric number is 6. 6 is for which hybridization? sp3d2. 1, 2, 3, 4, 5, 6. Yes, so it is sp3d2. And what did I mention? sp3d2 always has an octahedral geometry. It has an octahedral geometry. Okay, so it has an octahedral geometry. Now, how does it look like? Let me draw. This is the shape, I is in the middle, F, 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 F. Okay, there are only 5 F atoms, so we can only draw 5. So, there is only one lone pair left. Only one lone pair. And since there is only one lone pair, how can lone pair repulsions take place? Lone pair repulsions cannot take place. So, the first option is incorrect. There is only one electron, one lone pair. Okay. Now for B. Now for option B, we have SF4. We have SF4. Now sulfur atom over here is the central atom. So sulfur atom is in the same group as the oxygen atom. So it has number of valence electrons of 6 plus 4 atoms, 4 fluorine monovalent atoms, which totals up to number 10 by 2, which is 5. So 5 is the number for which hybridization? sp3d2. sp3d2, because one is 3p and 2d. So this adds up to sp3d. I'm incorrect. Yes, it was sp3d. So one is 3p and 1d. Okay, so let us see how it gets formed. Sulfur is in the middle, and there is a very important rule for sp3d orbitals. The rule is that the important rule over here is that the most electronegative atoms occupy the axial position. They occupy the axial position in the molecule in trigonal bipyramidal or TBP. Trigonal bipyramidal, we have written it in short form. So that is TBP. Okay, so what is the important rule over here? And most electronegative atoms occupy the axial position. So that is why it is very important for us to know what is an axial position. You can see that trigonal bipyramidal normally looks like this. So there are three positions over here, and these 3 positions, let us call them X. These 3 positions are known as the equatorial positions. These are known as the equatorial positions. And these 2 positions over here, okay, these are known as equatorial positions. Why? Because they are 120 degrees apart from each other. They are in the same plane. They are in the same plane, just like trigonal planar. I hope you remember about trigonal planar. I have talked. So these are in the same plane. So they are same plane. So these are equatorial position, and these 2 positions are axial position. These 2 positions are axial position. So now what happens? I have only 4 fluorine atoms. Now I have to fill up these 4 fluorine atoms in some way. So fluorine atoms, where will I put them? Will I put them first in the equatorial position or in the axial position? The rule is that the most electronegative atoms should occupy the axial position in a TBP molecule. So here the most electronegative atoms is fluorine. Even fluorine is the most electronegative atom in the entire periodic table. So in order to draw this structure properly, let me draw add another page. So we had SF4. So the fluorine atoms, like the rule said, it has to, since it is the most electronegative atom, so it is occupying the axial position first, and then the other 2 fluorine atoms which are left, they occupy the equatorial position, because there is no other position left. We have to place them in the equatorial position. So you can clearly see there is one position, equatorial position, which is left. There is only a lone pair of sulfur electrons, and since there is only one lone pair, so no lone pair repulsion, no lone pair repulsion. And since there are no lone pair repulsions, so this option is also incorrect. So let me go back to my question. Yes, SF4 is also incorrect. Now let us talk about XCF2 and CLF3. Let us do that quickly. XCF2 and CLF3. For XCF2, which one is the central atom? Xenon is the central atom. Xenon is a noble gas element. So what are the number of valence electrons over here? It is 8. And what are the number of valence electrons of fluorine? it is not valence electrons, but is the monovalent, is it a monovalent atom? So yes, it is a monovalent atom, so its contribution is 1. So 1 into 2 is 2, right? So now 8 plus 2 is 10. 10 is the total steric, 10 is the total number which is divided by 2, and it is 5, which is 5 is the steric number. So now this steric number 5, so it corresponds to which hybridization? sp3d. Okay, so let us draw XCF2. sp3d is what? TBP, trigonal bipyramidal. So TBP has two positions, like I showed you right now. It has two positions. It has equilateral position and as well as axial position. So since there are only two fluorine atoms and fluorine is the most electronegative element in this compound, so the fluorine atoms have to occupy axial positions. We will not start placing fluorines in the equilateral positions. It will occupy axial position mandatorily. So we can clearly see over here that the equilateral positions are left vacant. And since the equilateral positions are left vacant, so what happens? This structure is linear. You can see the geometry over here. The geometry over here is TBP, trigonal bipyramidal, TBP, but the shape over here is linear. Geometry will never change. Geometry will always remain the same. Whatever is the number, steric number, and whatever is the hybridization corresponding to that, the geometry will always be the same. If it is sp3d, it has to be TBP, but the shape of the molecule will always change depending on the number of atoms and many other factors. The shape over here, you can clearly see there are only 3 lone pairs and there are only 2 fluorine atoms. So you can't really say it is a trigonal bipyramidal shape. The shape will obviously look linear to us. Okay, but since we know the geometry is TBP, so we know the shape is as the hybridization is sp3d. It is not sp, because sp is also linear. So don't get confused between linear and all, between sp and sp3d. sp is also linear, but in that case shape and geometry both are linear. But in this case the shape is linear but the geometry is TBP, because there are not enough fluorine atoms in the molecule. I hope you get it. Okay, so here we can clearly see the lone pairs are very close to each other. They are about 120 degrees apart. So we have a huge LP repulsion, or lone pair repulsion. Why? Because there are 3 sets of lone pairs. And what about over here? We have ClF3. ClF3, there are 7 chlorine atoms and there are 7 valence electrons in fluorine atom. And how do we understand it is valence electron? It is the central atom, because fluorine is the only one and fluorine is 3. That's why we understand that chlorine is the central atom probably. So chlorine has 7 valence electrons plus 3 monovalent atoms are there. So 7 plus 3 is 10 by 2, which is 5. So again it is sp3d, which is TBP or trigonal bipyramidal geometry. Let us draw that again quickly. Cl. Now fluorine has to occupy the most electronegative, since it is the most electronegative element, it has to occupy the axial parts. So F, and only one fluorine is left, it has to occupy the equatorial position. So there are 2 more electrons, the lone pairs left. So 2 sets of lone pairs are there and they also carry out lone pair repulsion. But what is the answer over here? The answer over here is, since you can see clearly in XGF2, there are 3 lone pairs, there are 3 sets of lone pairs. So lone pair repulsion in XCF2 is greater than the lone pair repulsion in ClF3, because there are 3 sets of lone pairs over there and the sets of lone pairs in ClF3 is 2. Okay. So let us get back to our question, and we have finally got our answer. XCF2 is the answer. Okay. Moving on over here. Okay, so the dipole moments of CCl4, CHCl3 and CH4 are in the order. So what is dipole moment at the beginning? We have to discuss what is dipole moment. Dipole moment is mu is equal to Q into D, or charge into distance, but we don't require this formula right now. We just need to understand how to identify the dipole moment. We have 3 molecules over here. We have CCl4, we have CHCl3 and we have CH4. So what to do over here? CCl4, let us see CCl4. CCl4 is a tetrahedral molecule. I just told you, explained how to find out if something is tetrahedral or trigonal, bipyramidal. I have just explained VSEPR to you. Now what happens in CCl4 is how to find out the dipole moment of any molecule. You can clearly see the dipole moment in any molecule, I am showing a simple molecule like HF. So the arrow of dipole moment goes like this. So the arrow goes from the most electropositive element over here, which is hydrogen, to the most electronegative element, which is fluorine over here. And the arrow of dipole moment goes like this. There's a cut over here. There's a cut in between at the end of the arrow. Okay. So the dipole moment arrow, it is represented like this. So what about CCl4? CCl4, as we know, 4 plus 4 is 8. 8 by 2 is 4, which is tetrahedral sp3. So it is sp3 hybridized. Now we have nothing to do with the hybridization. It is important for this. The structure is very important for us to find out the dipole moment of the molecule, the resultant dipole moment of the molecule. In this case, one arrow is going over here. One arrow goes over here, one arrow goes over here in this direction, and one arrow goes over here. Why? Because carbon over here is electropositive and chlorine over here is electronegative. So as a result, the resultant dipole moment is 0. Why is it 0? Because the dipole moment over here, the dipole moment which is going, the CCl dipole which is going in the upward direction, it is directly counteracting 3 dipole moments. The resultant of these the 3 dipole moments resultant is in the downward direction. So this downward direction, the dipole moment which is going in the downward direction, it is directly cancelling the dipole moment which is going in the upward direction. So the resultant mu is 0. Okay. So the mu is 0 over here. Let us look at CH4. CH4 also has a tetrahedral structure, and in this case there is a twist. The arrow direction will be different, because over here the hydrogen is the most electropositive element. So the arrow goes from hydrogen to carbon. Similarly, arrow goes from hydrogen to carbon, hydrogen to carbon, and hydrogen to carbon. Okay. But over here what happens is the same thing. The arrow, the resultant of this CH bond, it is in the downward direction, and the resultant of these 3 CH bonds are in the upward direction. So they are directly cancelling out each other, and the resultant mu is 0. So CH4 mu and CCl4 mu will be same. So now what about CHCl3? CHCl3, it is self-explanatory that there are 3 chlorine atoms. This is also tetrahedral, and there is 1 hydrogen atom. So now what happens is that chlorine is more electronegative, and compared to that carbon is electropositive. So the dipole moment arrow is from C to Cl, Now hydrogen is more electropositive than carbon. So the dipole moment arrow is from hydrogen to carbon. So resultant dipole moment arrow is in the downward direction. So as a result, mu is very high. The dipole moment is very high. The resultant is not getting cancelled over here. So among these 4 examples, we can clearly see CH4, the option D. CH4 is equal to CCl4, which is 0, and it is always obviously lot less than CHCl3, because the CHCl3 dipole moment is high. We have just seen how. And this question came in JEE 2020. So it is very easy. You can clearly see it. No need to fear. Okay. So now the 7th question. The total number of lone pairs of electrons in I3 minus ion is what? So I have just explained VSEPR theory to you. I3 minus looks like what? What is the central atom? I know you can get confused because it came in JEE 2018. So you can get confused. There are 3 iodine. Which one is the central atom? So just take 1 iodine. Since there are 3 iodine, 1 has to be the central atom, right? So just take 1 iodine, and iodine is in the same group as fluorine. So iodine, the number of the central atom, which is the iodine over here, one of the iodines, it has a number of valence electrons of 7, plus there are 2 other iodines which we can add up. Okay, and here what happens? It is the molecule is charged. It has a negative charge. So if we see a negative charge, we always add +1. And if we see a positive charge, we always deduct -1. And if there is 2 negative charges, we add +2. If there are 2 positive charges, we deduct -2. Okay. So since the central atom is iodine over here, the number of valence electrons is 7, and the 2 other monovalent atoms were linked to it. So they are monovalent, so they each contribute 1. So 1 plus 1 is 2, and this 1 comes from the negative charge, which is 7 plus 2 plus 1 is 10 by 2, which is 5. So this is sp3d, and this is sp3d is trigonal bipyramidal geometry. So how does it look like? I, and since the I is a central atom, and since The other iodine atoms are also electronegative, so they will occupy the axial position as usual. So the equatorial position will not be filled by anyone, it will be vacant. So what will be getting? We'll be getting a linear structure. But the question was what? The question was the total number of lone pairs of electrons in I3 minus ion is what? So there are 3 sets of lone pairs. 1, 2, 3. So the total number of lone pairs is 3. So you can clearly see that JEE mains questions are very simple. If you once get to know how to form the structures, it is very simple. Okay. So now the next question, it came in JEE 2016, the species in which the N atom is in a state of sp hybridization is NO3 minus, NO2 plus, NO2 and NO2 minus. So how will you again understand? You don't have to draw the complicated Lewis-Druss structure. Just follow the VSEPR, whatever trick I have taught you for the VSEPR theory. What was happening over here? The nitrogen atom over here for NO3 minus ion, let us take the example of that. For NO3 minus ion, the nitrogen atom over here is the central atom and the number of valence electron is 5. So 5 plus, I just explained one thing. Okay, if I have forgotten, no, I did explain it. It was there somewhere. Let me just check. I did explain it somewhere. If I have not, then let me explain. If there are divalent atoms like oxygen, sulfur, so their contribution, since they are divalent, they are not monovalent, so their contribution to the steric number is 0. So oxygen, sulfur, their contribution to the steric number is 0. So we do not add anything for oxygen. So there are 3 oxygen molecules and everybody has a contribution of 3 into 0 is 0. Plus there is one negative charge, so plus 1 is equal to, what is the answer? 5 plus 1 is 6. So 6 by 2 is 3. So 3 is what? 3 is sp2. sp2, right? So how does sp2 hybridization look like? What was the question in the beginning? Okay, so there are a species in which the N atom is in a state of sp hybridization. So we don't require to draw the geometry. So it is sp2 hybridization, right? Okay. So we have already obtained the central atoms hybridization over here, which is sp2. Now about NO2, let us find out. NO2 central atom is N. The central atom has valence electrons 5 plus 2 doesn't give any contribution, so 0. So it is tricky. So it has 5 by 2, which is 2.5. Okay, so it has something in between. So it has a partial hybridization. So we'll be discussing it later. So now over here, so this is not sp. You can say it is 2.5. It is between sp and sp2, right? So it is not completely sp. So now let us go to option C, which is NO2 plus. So here the central atom is again 5. So 5 plus the central atom is nitrogen, which has the valence electron 5, plus the divalent atom oxygen doesn't give any contribution to the steric number, and then we have a positive charge. So I just mentioned that if there is a positive charge, we deduct minus 1. So 5 minus 1 is 4, by 2 is 2, which means this 2 is what? sp hybridization. So now we have obtained our answer. NO2 plus is the answer. If you want to find out the answer for NO2 minus, let us find out. NO2 minus is nitrogen is central atom, 5, 2 doesn't give any contribution, so only minus 1 has a contribution. So minus 1, sorry, plus 1 because it is a negative charge. 6 by 2, which is 3. 3 is sp2. So we can clearly see the answer is NO2 plus because it has a hybridization of sp. Okay, this is the answer. This came in JEE 2016. So I guess you will be able to understand now properly, very easily, how to find out the steric number and how to find out the hybridization. Okay. Okay then. Now this is a question which came in NEET 2020. The manganate and permanganate ions are tetrahedral due to the pi bonding involves. Okay. So before answering this question, what is the meaning of permanganate and manganate ions? Let us see. Permanganate and manganate ions. Manganate is manganate ion. Manganate is MnO4 2 minus, and permanganate is MnO4 minus. So that is the difference between the two ions. So now the question is that the manganate and permanganate ions are tetrahedral due to what? Why they are tetrahedral? So why they are tetrahedral? Okay. So let us see why they are tetrahedral. Let me add one page. Okay. So over here, MnO4 2 minus. Let us see over here. Manganese. What is the electronic configuration of manganese? The electronic configuration of manganese is argon. Then we have 4s2. Then we have 3d5. This is for pure manganese. Okay. So now the oxidation state of manganese over here, if you are able to find out, it is 4 2s are 8 plus 6. Plus 6. The oxidation state of manganese over here is plus 6. So in the oxidation state chapter, it is the oxidation state can be easily found out. We'll be discussing it in the other classes. If you want me to discuss, if the oxidation state is X over here and oxide has a charge of -2, so X minus 2 into 4 is equal to 0. So no, X minus 2 into 4 is -2. So X minus 8 is equal to -2, X is equal to 8 minus 2, which is plus 6. So this is how you can find out. And why? How did we get this -2? Because the total charge of the molecule was -2. That's why. Okay, so manganese plus 2 then will have an electronic configuration of argon 3d5. Okay, why only 3d5? Because the two electrons from manganese, it was emitted from, it escaped from the 4s orbital first. Now why it escaped from the 4s orbital? It is due to the n plus z rule, and there are many other factors, but we will not be discussing because we will be discussing these things in the atomic structure. You just need to know that whenever there is an electron which is escaping the orbital, which is escaping any d orbital, any any atom from the transition metal, so it always escapes from the 4s orbital. Okay, so that is the main thing over here. And now what happens is that manganate, so it is MnO4 2 minus. So what was the question is that why it is forming a tetrahedral structure. So let us draw Mn. There is OOOO. Okay, this negative charge, and there are two double bonds. There are two double bonds and two negative charges. Fine. So these two negative charges, they are in the resonance. So this is a very good example of a tetrahedral moiety. And in MnO4 minus, similarly we have a manganese in the middle, and we have O minus, O double bond O, double bond O, double bond O. It somewhat looks like this. So there is only one O minus, and here we have two O minuses, and that is why we have this moiety. So both are tetrahedral in nature, TD. Okay. So now what was the question? The question was why they are tetrahedral. The reasons are given. Let us read them out. The pi bonding involves overlap of p orbitals of oxygen with d orbitals of manganese. There is no pi bonding. The pi bonding involves overlap of p orbital of oxygen with p orbital of manganese, and the pi bonding involves overlap of d orbital of oxygen with d orbitals of manganese. Okay, so let us first understand this one thing. Oxygen has an electronic configuration of 1s2, 2s2, 2p4, right? So it has the electronic configuration of only it has only a p orbital as its valence electron. So it has no d orbitals. So if it has to carry out p pi d, if it has to carry out bonding, so what it will do? It will donate electrons. It will resonate with the help of electrons in its p orbitals. Oxygen doesn't have any d orbitals. It will only use electrons of its p orbitals to carry out resonance. So manganese, on the contrary, I have just shown that the valence electron in manganese is d. So over here, manganese will only accept electrons in d orbitals, and oxygen will donate electrons from the p orbitals. So the bonding is p pi d pi bonding. Okay, so manganese accepts in its d pi, and in its d orbital, and oxygen donates to the from the p orbital. So from there you can clearly understand the answer, which is the pi bonding involves overlap of the p orbitals. Only oxygen has only p orbitals with the d orbitals of manganese. Okay, so that is the answer. Okay, now okay, so this came in NEET 2020. Now this one, isostructural species are those which have the same shape and hybridization. Among the given species, identify the structural pairs. So I guess I will not discuss this much because we have very short time. So see, A has NF3, BF3. So NF3 has what? NF3 has what structure? 5 plus 3. 5 plus 3 is equal to 8 by 2, 4. 5 plus 3 by 2 is 8 by 2, which is 4, which is tetrahedral. And what about BF3? BF3 has, the central atom is boron. So it is 3 plus 3 by 2, which is 6 by 2, which is 3, which is what? 3 is sp2, which is trigonal planar. Trigonal planar. So they are not isostructural. So this is incorrect. What about BF4 minus and NH4 plus? BF4 minus and NH4 plus. Let us find out. B 3 plus 4 plus 1, which is 4, 5, 6, 7, 8. 8 by 2 is 4, which is tetrahedral. And for NH4 plus we have 5 plus 4 minus 1, which is 5 plus 4 is 9 minus 1, 8. 8 by 2 is 4. So we have tetrahedral. So we can clearly see the option B is isostructural. Since only one option is correct, we don't need to. If you want to see, you can check the other two compounds as well, but they are not the answer. Okay. So only BF4 minus and NH4 plus is the answer. They are isostructural to each other because they both are tetrahedral geometry. Okay, now we reach at a very important point, which is the molecular orbital theory, and lots of questions are asked from the molecular orbital theory. So the molecular orbital theory is, the main thing over here is atomic, when two atoms come together to form a bond, atomic orbitals of one atom, of A atom, you can say, overlaps with the atomic orbitals of atom B, and it forms a molecular orbital. It forms two molecular orbitals. Okay, just a minute. Yeah, they form two molecular orbitals. One is bonding molecular orbital, MOT, molecular orbital. I am writing it in a short form. Bonding molecular orbital and anti-bonding molecular orbital, or ABMOT. I hope you are aware of this, because since I am carrying out a marathon, so I am not going into the details of this. Okay, so the number of atomic orbitals combining to form to form the molecular orbitals, it is the equal. So the number of atomic orbitals has to be equal to the number of molecular orbitals formed. Okay. So and it is formed with the help of LCAO, that is linear combination of atomic orbitals. I am not again going to the details because we don't have enough time. So the main thing over here is, why do we require MOT or molecular orbital theory? To find out the bond length, bond length order, then the bond order, then the bond strength, and stability of molecules. So there are two things which you need to keep in mind in molecular orbital theory, which is there are two types of systems. There is a 14 electron system below or equal to 14 electron system, and the another is the above 14 electron system. There are two types of molecular orbitals in both the cases. So let us discuss that. Okay, equal to or below 14 electron system, the molecular orbitals look like what? They look like this. Let us take the example of carbon. Okay. So carbon is what? Carbon or C2. Yes, C2 molecule. So C2 molecule looks like what? There are 6 in one carbon atom. There are 6 there are 6 electrons, not valence. There are 6 electrons. So 6 into 2. 6 into 2 is 12 electrons, right? So there are 12 electrons over here. So let us draw them. Okay. So this is the energy. This is the energy. So over here we have the 1s. We have the 1s of carbon, one carbon. This is 1s of one carbon atom and the 1s of another carbon atom. Okay, so the 1s, then we have the 2s. The 2s of carbon atom is bonding with the 2s of another carbon atom to form two molecular orbitals, bonding and anti-bonding. So this is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Now we have the 2p orbital. 1, 2, 3, 1, 2, 3. So they form this. Now something like this. Okay. So you can clearly see, this is just a recap because I know you know these basics, is that if the atom, if the molecule is below 14 electron system, then the pi orbital, when the 2p of one carbon and the 2p of another carbon, they overlap, they form the pi x and the pi y, and the pi z is above this. So 2p and 2s mixing takes place, and since the 2p and 2s mixing takes place, our pi orbitals decrease in energy and they come below the pi z orbital. And the this is the pi star x, pi star y, and this is the sigma. This is the sigma star. Sorry. Yeah, sigma. Okay. So now what happens over here? So now what happens over here? So this is the 14 electron system. Now equal to or below the 14 electron system. And if it is above the 14 electron system, how does it look like? If it is above the 14 electron system, for the example of O2 molecule. So O2 molecule is what? 8 into 2, which is 16 electron system. This is a 16 electron system. Okay, one thing I did not discuss in carbon molecule is the electron placement. Yes. So there were only 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so there are 12 electrons over here. Now, since there are 12 electrons over here, you can see that what is the bond order of this carbon atom or C2 molecule? Bond order is number of bonding at electrons minus number of anti-bonding electrons by 2. This is the formula for bond order. So number of bonding electrons is 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 1, 2, 3, 4. So 4 anti-bonding electrons by 2, which is 4 by 2, which is 2. Okay, so this is clear to you that the bond order is 2 for this C2 molecule. So now let us go to the above 14 electron system, that is 16 electron system. What happens over here? So we have another MOT like this. So there is 1s, 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 there is 2s, 2s. They are of all oxygen atoms. And then we have 2p. The pi orbitals, you can see there is no sp mixing over here. This is 2s, 2s, this is 1s, 1s, oxygen atom, this is the energy coordinate, this is the 2p, this is the 2p, and you can clearly see that the sigma is over here, sigma star is over here. This is pi x, pi y, pi star x, pi star y. Okay. So this is clear to you. Now oxygen 16 electron system, how will we fill it up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the bond order over here is number of bonding electrons minus number of anti-bonding electrons by 2. So number of bonding electrons is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 minus 1, 2, 3, 4, 5, 6, 6 by 2, which is 4 by 2, which is 2. So the bond order over here is also 2. Okay, I hope you understood how to find out the bond order, and how to draw the orbitals. So this is an oxygen system where the 2p mixing is not happening, so the sigma is below the pi. But in case of a 14 electron system, the sigma is above the pi. Okay, so the sigma gets destabilized. Okay, so now let us solve the questions. Among in JEE 2019, what we received such a question: among the following, the molecule expected to be stabilized by anion formation. So first we need to know. See, it is not possible for you to draw many electrons draw lots of orbitals or MOTs for all the atoms. So what you do mainly, we try to simplify the MOT. How? For C2, we just saw for C2, we drew for C2. So we know that sigma 1s and sigma 2s. In maximum type of molecules, the sigma 1s and sigma 2s is filled. So we ignore the sigma 1s. Usually we ignore the sigma 1s. We try to fill up the electrons from sigma 2s. We just ignore sigma 1s. Okay. So sigma 2s we just write the notation, main notation, sigma 2s and sigma star 2s. You know, first you will have sigma 2s, then you will have sigma star 2s, then you will have pi, for C2 molecule below 14 electron system, you will have pi x and pi y, then you will have sigma. Okay, so let us see, let us draw this. Okay, sigma 2s, sigma star 2s, then we have pi x, or just pi x, pi y, and then we have sigma, then we have pi star. Okay, the pi star, it doesn't go till there. So then we have 1 2 3 4, it was a 12 electron system, right? It was a 12 electron system. So 12 minus 4, because we have ignored the 1s orbitals, so 12 minus 4 is what? 12 minus 4 is 8. So 1 2 3 4 5 6 7 8. Okay, so till here we are getting it. So what is the answer? So what is the answer? What is the final answer of this compound? The question was that among the following, the molecule expected to be stabilized by anion formation. So we have to add one electron to C2 to make it C2 minus. So if we add one electron, we will get one electron in the bonding molecular orbitals, and since it is in the bonding molecular orbital, so the bond order over here is 1 2 3 4 5 6 7 1 2 3 4 1 2 3 4 5 6 7 7 minus 2 by 2. What is the bond order now? 7 2 1 2 3 4 5 by 2, which is 2.5. You see, you don't need to do so much. You have to see ki after addition of an electron to the corresponding molecule, is the electron entering the bonding molecular orbital or the anti-bonding molecular orbital? If it is entering the bonding molecular orbital, what we do? We call that the addition of anion is stabilizing. Okay. In case of C2, we can say it is entering the bonding molecular orbital, and so it is stabilized. It is expected to be stabilized by anion formation. So this is C2 is the answer. But in case of F2, if you do the similarly F2 and O2, you will see the electron is entering the anti-bonding molecular orbital, and if it enters the anti-bonding molecular orbital, the bond order decreases, and if the bond order decreases, the bond strength decreases, and if the bond strength decreases, the stabilization of the molecule decreases, and that only happens if the electron enters the anti-bonding molecular orbital. So this is very important for you to know. Okay, it's extremely important. So the answer was C2 over here. It was the first one only. Now, okay, so then there was one thing which we did not discuss is NO. What is the MOT of NO? So this is another thing which you need to remember. MOT of NO and MOT of Cn minus. So NO resembles the O2 molecule, the O2 MOT. So whatever was the O2 MOT, that is the MOT of NO. Okay. And what about Cn minus or Cn in general? It resembles the C2 molecule MOT. So whatever was the MOT of C2 molecule, that is the MOT of Cn. Okay, so you don't need to worry. Okay, so let's move on to the other questions. So consider the following species Cn plus, Cn minus, NO and Cn. Which one of these will have the highest bond order? Okay. So which one of these will have the highest bond order? We have now discussed that NO, just a minute. Yeah. So we have just now discussed that NO resembles what? NO resembles your O2 molecule. So if it resembles O2 molecule, we are just ignoring the 1s. So we just start writing from 2s. So sigma 2s, what it was? Sigma 2s, sigma star 2s, then we have pi x, pi y, then sigma 2p, we have the sigma 2p, and then pi star x, pi star y, then sigma star. Okay, so we have the sigma star 2p. Okay, so now since we have what is the total number of electrons over here in NO? NO is 7 plus 8, 7 plus 8, which is 17. 7 plus 8, 15. So 15. So 15 minus 4, because we are eliminating the 1s. So 15 minus 4 is 11. So total number of electrons in NO is 11. So let us start filling them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And since it follows the oxygen molecule, sorry, I made a mistake, and sigma 2p should be over here. Sigma 2p over here. So let me write that down. Sigma 2p, and we have 2 electrons over here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11, the last one should have only 1 electron. Only 1 electron. Okay. Okay. So now what is the bond order? We have to find out the bond order. Bond order is equal to 2, 3, 4, 5, 6, 7, 8. So 8 minus 2, 3. 8 minus 3 by 2, which is number of bonding electrons minus number of anti-bonding electrons by 2. Okay, so 8 minus 3 is what? 5. 5 by 2 is 2.5. So bond order is 2.5. What about Cn minus? We just discussed that Cn minus MOT resembles which? C2 molecule. So Cn minus has total number of electrons how much? 6 plus nitrogen is 7 plus 1. So 14. It is a 14 electron system, and since it is a 14 electron system, it follows a C2 molecule MOT, and we have to draw it accordingly. And 14 minus 1s orbitals, we are not considering them for, currently. It is 10 electrons. So 10 electrons we have to place them. Sigma 2s, sigma star 2s, sigma 2p, then we have, this is the sigma, this is pi 2p, we will have a pi orbital over here. So pi 2p x, pi 2p y, then we have sigma 2p z, and then we have pi star 2p, pi star 2px, pi star 2py, then sigma star 2pz. Okay, so let us fill them. We have 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what is the bond order over here again? Bond order is number of bonding electrons 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 2, which is by 2, which is 8 minus 2 is 6 by 2, which is 3. So Cn minus is a bond order of 3 in this case, isn't it? So it is a bond order of 3. So which means it is a pretty high bond order. So in the same atom, same configuration only, let me find out Cn. So Cn minus is 10 electron system. So Cn will be 9 electron system. So what do? We remove 1 electron and we write it 1. So the bond order will be, since we are removing that electron from the bonding molecular orbital, so bond order of this was Cn minus, bond order of Cn will be what? Bond order of Cn will be 2, 3, 4, 5, 6, 7. 7 minus 2 by 2, which is 5 by 2, which is 2.5. So this decreases from 3, right? So Cn is not having the highest bond order, and Cn plus, we are removing another electron from the bonding molecular orbital, so it will become more destabilized. So it will the bond order will become more decreased. So as a result, what happens that we don't have to calculate much further, just if you get the answer, take it. So Cn minus has the highest bond order. Okay, this came in NEET 2018. Okay, this also came. Now this, which are the following pairs of compounds? Which are the following pairs of compounds are isoelectronic and isostructural. So isoelectronic means same number of electrons and isostructural means same structure. Okay, let us find out. We have again discussed this before as well. Okay, just a minute. Yeah. So we had discussed this before. So answer, I'm just telling you how to find out the answer. Tellurium. Tellurium is in the oxygen group. Oxygen, sulfur, selenium, polonium, tellurium. Okay, so oxygen, so tellurium TeI2, it has a valence electron 6 plus iodine is what? Iodine monovalent, so 2 is 8 by 2 which is 4. It is tetrahedral and sp3 hybridized. Okay. What about HCF2? HCF2 is 8 plus 2 which is 10 by 2 which is 5. Okay, the steric number is different. So their hybridization will also be different. So they are not isostructural. So this is incorrect. B. IBr2 minus, which is 7 plus 2 plus 1 which is by 2. 7, 8, 9, 10 by 2 is 5 which is TBP, which is sp3d. What about HCF2? It is 8 plus 2 by 2 which is 10 by 2 which is 5, and this is TBP again. So this is isostructural. So is it isoelectronic? Yes, isoelectronic, because IBr2 minus, you can clearly see that TBP, they are both forming the same structure. They are both sp3d hybridized, and if the central atom has 7 valence electrons, the bromine also contributes 2 electrons and it is -1. So minus 1 charge. So the total is 7, 8, 9, 10. 10 electrons over here. Here also in HCF2, 8 electrons of central atom plus 2 electrons of fluorine, which is also 10 electrons. So both are having same number of electrons, outer valence electrons. So this is the answer. The second answer is the answer. So we have already obtained our answer. So this is an MCQ. So if you obtain the answer, you don't have to record the others. Okay. Which are the following set of molecules will have the zero dipole moment? Okay. So boron trifluoride, hydrogen fluoride, carbon dioxide, and 1,3-dichlorobenzene. Which one has zero dipole moment? Again, this is the question of dipole moment. So let us find out. Boron trifluoride. Boron trifluoride is BF3. BF3 looks like what? BF3 looks like this. I have already explained it before. How will we draw out a dipole moment over here? From boron to fluorine, and boron to fluorine. Because boron is more electropositive than fluorine. So it is a dipole moment of 0. For hydrogen, we have been asked to find out the zero dipole moment. Okay, so boron is correct. Now we have hydrogen fluoride, we have HF. HF cannot have dipole moment 0, because you see the dipole moment is coming from hydrogen to fluorine, but there is no one to cancel it out. In boron, all the dipole moments are getting cancelled out, because the net upward dipole moment and the net downward dipole moment, they are cancelling each other out. But in HF, there is nobody to cancel out, so the mu is not equal to 0. In case of carbon dioxide, let us see, carbon dioxide is C double bond O, C double bond O. So the electron of this is going over here, and because carbon is more electropositive than oxygen, and this arrow is going over here. So the mu over here is also 0. And about 1,3-dichlorobenzene. So 1,3-dichlorobenzene, let us look. Okay. 1,3-dichlorobenzene. So if this is the first position, this is the third position. So this is again not, the mu is not equal to 0. So this is incorrect. So let us look. Nitrogen trifluoride, beryllium difluoride, water, 1,3-dichlorobenzene. We also have any option with 1,3-dichlorobenzene, just cross it out. This is also 1,3-dichlorobenzene, so this we will cross it out. So because we need to find out molecules which have zero dipole moment. And boron trifluoride, beryllium difluoride, carbon dioxide, here we have boron trifluoride, beryllium difluoride. We'll look at this again. Then again we have, okay, C and D molecule. Let us see which one is correct. We have boron difluoride and C. Let's see what we had. Boron trifluoride we just explained. Beryllium difluoride. Let us see that. Beryllium difluoride. BeF2. Okay, so beryllium is 4 plus 2 is 4 plus 2 6 by 2, which is 3. Sorry, beryllium is 2, sorry, it's 2 plus 2, which is 4 by 2, which is 2. So 2 is sp, which we mean is linear. So f. So it is very important to know the hybridization. So beryllium is more electropositive than fluorine. So it is a net mu of 0. So it is a net mu of 0. And now what do we have? BF3 we have discussed, it is mu is 0, beryllium difluoride is 0, carbon dioxide also we have discussed is 0, and 1,4-dichlorobenzene. How does it look like? It is 1,4-dichlorobenzene, this is a benzene molecule, and the chlorine is, if this is the first position, this is the fourth position. So the mu, the dipole moment over here and the dipole moment over here is cancelling each other out. The CCl dipole moments are cancelling each other out. So the mu is 0. Okay. So the third question is, the third option is the correct one. Okay. So now this is the last question which we'll be discussing right now. Read the following statements and choose the correct option. So the PO bond length order is this. So there are 3 options and we have been asked to choose the correct option between these 3 options. Okay, so they all 3 can be correct, the first 2 can be correct, only one can be correct. Let us see. So PO bond length order is this. So let us find out if the first one is correct or not. So we have been given 3 molecules, PO4 3 minus, HPO, what was it? Let me see. Let me check. It was HPO3 2 minus and H2PO2 minus. 2 minus and H2PO2 minus. Yeah, let us check. Okay, the bonded order, it was in this order probably. Okay, so it was like this. The structure was like this. And here the HPO3 structure should be like this. Hydrogen O minus, O minus. And over here phosphorus double bond O, H, and we have O minus. Okay, so you can clearly see this is PO4 3 minus. So there are 3 O minus atoms. So usually what happens is that it is obtaining resonance from 3 oxygen atoms, 3 more oxygen atoms. So each bond length is increasing. So the resonance hybrid kind of looks like this. There are 4 oxygen atoms and the bond length is increasing due to resonance, because each and every bond over here has partial double bond character. Partial double bond character due to resonance. And since the resonance over here is much more profound, because there are 4 oxygen atoms which are undergoing resonance. So since it is a partial double bond character, the trueness of the double bond character is decreasing, and that is why the bond length over in PO4 3 minus is the highest. Because if it resembles a single bond, it will have a longer bond length. Single bond has a sigma bond has a greater bond length than pi bond, isn't it? That is why. But what about HPO3 2 minus? So there are only 2 oxygen atoms which are undergoing resonance. So as a result, the double bond character, the resonance is less. The resonance over here in the second structure is less. As a result of that, since the resonance is less, so the double bond character is more as compared to the first structure. The double bond character of this oxygen is greater. Okay, and what about this? This oxygen atom over here, it only receives resonance from only one oxygen atom. So it has a higher double, since the resonance is decreases more over here. So over here what we say, the double bond character increases a lot. Okay, so this is the reasoning. The first option is correct. So due to increased resonance, the double bond character of the oxygen atom decreases, and that is why our bond length increases. So this leads to the increase in the bond length. If the double bond character decreases, the bond length increases. Okay, so let us go back to the question. Okay, so now this one is correct. So let us see. Okay, in CH3F and CF3H, so which the bond angle of theta 2 is greater than theta 1. Yes, both are tetrahedral, but why bond angle of theta 2 is greater than theta 1? Because over here both are sp3. Both are sp3 over here. But carbon is, since fluorine is more electronegative, so carbon has a tendency, it is very important, carbon has a tendency to bond with fluorine with its more, with its higher p orbital, with its orbital which has a higher p character. So over here if I show you, so in CF3, CFHH and CHFFF. So in such a case, carbon both are having sp3 orbital, but since fluorine is more electronegative, has a higher chi, so carbon uses p orbital of higher p character. Carbon uses orbitals of higher p character to bond with the fluorine atom, and over here the carbon utilizes, in case of CHF3 or CF3H, carbon utilizes orbitals of higher s character, higher s character. So one thing which you need to remember is, higher is a percentage s character, so higher is the bond angle, higher is the bond angle. So bond angle increases, bond length also decreases, and bond strength increases. So the carbon is bonding in this case, in case of CF3H, the carbon is bonding with a greater, with hydrogen atom with a greater s character orbital. So as a result, the bond angle in case of CHF3 increases. So theta 2 is greater than theta 1. This is the answer. And what about this? What about the last question? Between C2H2 and C2H4, CH is stronger in C2H2, right? Because C2H2 is alkyne, and alkyne is, we have discussed, sp hybridized, and in C2H4 it is alkene, and alkene is what? It is sp2 hybridized. Obviously in sp hybridization we have this, we know that if percentage s character is 50%, okay, but in this case the percentage s character is decreased, less percentage s character as compared to sp, and as a result of that the ch, higher the percentage s character, I have just written it over here, higher the percentage s character, higher is the bond strength. So the bond, ch bond is stronger in C2H2 because it is sp hybridized. I hope everything is clear with you, and I will be coming up with more questions and more marathons in future regarding different chapters. Okay, thank you so much. And if you have any problems, issues, please write in the comment section. I will be attempting to help you out in each and everything. Thank you.